Okay, this homework takes a look at dynamic programming, and the first question here appears to be on the Huffman encoding tree. And the Huffman encoding tree is, the whole point of Huffman encoding is to try to find a short binary representation for a string or a bunch of characters. In this case, we've got this giant string, A, B, F, B, C, D, F, all of these letters, and we want to convert it into some kind of binary, 1, 0, 1, 1, 1, and we want that to be as small as possible. We don't want a massive binary file to encode this string. And what we could do is we could say, hey, A is equal to 0, 0, and we could say that the B's are equal to, let's say, 1, 0, 1, 0. And if we do something like this for all of the letters, and we just do it randomly, then we'll have a pretty long string, most likely, unless we get very lucky. But the goal behind the Huffman encoding is to see which of these letters occur the most frequently and assign them to the shorter encoding lengths. So we pick the letters that we don't see very often, like I think it doesn't look like there's very many E's, and we would give the E's a long encoding, like 1, 0, 1, 1, and we'd give letters that we see a lot, like A very short encoding, like the 0, 0 here I did by default. And that'll give us an overall shorter binary encoding of this string by using the letters we see the most frequently by having very short ones. So if we had a bunch of A's, it would just be, this would be 3 A's in a row. And if we had B's, they'd be very long, but that doesn't appear to be the case in this string. And so, in order to be able to do this, we need to find the occurrences of all of these letters so we can come up with this ideal binary encoding that'll give us the shortest possible binary representation of this string. So let me delete this real quick, copy it back. Now, we need to count up all of these letters. And since it's quite easy to be able to miscount, I copied this and I'm going to pasted it in here. We can see though that we've got blank spaces even though he said no spaces. So in Python it's pretty easy to get rid of it. We'll just do input.replace and we'll replace all of our blank spaces with nothing. Now here I've got a little dictionary where I'm storing the occurrences of each of these letters. Every time I find a letter that I haven't added yet, I say I found it one time. So first time I find B, I say B is 1. And then next time I find B, if it's already in my dictionary, I add 1 to its occurrence. So next time I find B, I say, hey, now there's 2, then there's 3, 4, so on and so forth. And I do this for all of the letters. And I give this a run, and we can see here, we calculated all of the occurrences of each of the letters in this nice little dictionary. And now I'm going to copy this over. Also, this line is sorting it in increasing order to make it a little bit easier to read. And I'll head back here and paste this. And now we've got a little cheat sheet of all of the occurrences of the letters, and we don't have to try to count it up and make sure we didn't mess up. And so with the Huffman encoding, we want to create a binary tree that will have short paths to our nodes that have lots of occurrences and long paths, so like a 1, 0, 1, 1 or something like that, to our nodes with very few occurrences. So our A will be near the top of the tree and have something like 0, 0, and our E will be way at the bottom after a whole bunch of branches, and it'll have a much longer encoding. So let's try drawing that out. So first thing we'll do is we'll pick the 2 with the lowest with a number of occurrences. So we've got E with 3 and D with 4. I'll draw those basically in the middle here, I suppose. E has 3 occurrences, so we'll make a note of that so we don't forget. And D has 4 occurrences. And to keep things straight, you'll always want to put the lower occurrences to the left. It's a general rule of thumb is left children are smaller. You could do the opposite if you wanted, you just have to be consistent about it. And so 3 and 4 are our 2 lowest, and when we combine them, we get a total of 7. Now we look at what our lowest is left over. So we've used E and we've used D, and we've got a 7 of their combination, a 7 for F, and a 10 for B. The 2 7s are the lowest right now, so I'll go ahead and throw F down here with 7, and it will combine with this tree. And now this one's taken care of, and we look at the next 2 lowest. So 7 plus 7 gives us 14. So this has a total weight of 14 so far. Now we look and we've got 14, 10, and 13. Well, 10 and 13 are the 2 lowest, and they're both lower than 14. So we'll come over to the left, and we'll draw our B and our C. Our B has a value of 10, and our C has a value of 13. And we'll continue adding to this tree. So our B is taken care of, and our C is taken care of, and this has a total of 23. So now our values are 23, 14, and 16. So 14 and 16 are our next 2 lowest. I'll throw my A to the right here because it's more than 14. And then I'll draw this so it's now part of the tree. And this gives us a total of 30. And 16 is taken care of. All we have left is 30 and 23. So we'll combine these last 2 elements. And now everything has been fully connected to our tree. And by default, remember left side's always lower. So we'll put all of our 0s down the left path and 1s down the right path. So 0, 1, 0, 1. And we encode going backwards, so starting at the top here. So our A, I'll do these in alphabetical order. Our A will be 1, 1. Our B will be 0, 0. Our C will be 0, 1. D is now 1, 0, 1, 1. E is 1, 0, 1, 0. F is 1, 0, 0. Good Lord. And we can see, looking back at our occurrences, we've got very short strings for A, B, and C, and those were the 3 that had lots of occurrences. And D, E, and F have longer strings and much fewer occurrences. So overall, this encoding will give us a fairly short, relatively short, binary representation of this long string he gave us. And you can even see what the first part of it would look like. We've got ABF for the first 3 letters, so it would look like 1, 1, 0, 0, and then 1, 0, 0. This would encode the first 3 characters of that string. And it's already fairly short. If we had EEE, it would be much longer already. We'd have 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0. And we're already have a much shorter string than what we might have had we done a naive assignment and just kind of randomly picked them. So the Huffman encoding is really good at finding the minimum way to represent a string in binary that's easy to decode. That should handle that. Let me clear this out now. Next question, compute the edit distance and its length for London and Toronto. you must show the table constructed by dynamic programming algorithm. Okay. In this case, we want to convert the word London to Toronto and figure out how many operations that will take. Normally, with these algorithms, you have three operations. Draw a little cheat sheet here. You've got an operation to insert, which is usually when you go up in the graph, an operation to remove, which is when you go to the left, and an operation to replace, which is when you go diagonal. So I'll keep this here as a nice little note so we don't lose track. So this is insertion, this is replacement, and this is deletion. And hopefully it'll make sense as we draw this out. So let me draw all of our letters here. We've got London, I'll do London along the top, and Toronto down the side. All right, and I'll draw some lines real quick because this will have to be a full graph. So, won't be perfect since he wants you to graph out this whole representation of how this will look. It's a small column there, but all right, there we go. And actually, I want to move this down a bit and add a null. Okay, a little bit more space, and kind of want a null here actually. Let me scooch this over. Not the the neatest line. Let me fix this line here. This will be that. Okay, it'll make sense why I needed to have these null lines. Ugh. Have to cover this up. All right, it's beautiful. Oh, this little line to fix this. There we go. Because yeah, you need a null here that I left out to be able to see how to convert kind of a blank string for our base cases. All right, now that this is all beautiful, we'll draw this out a bit. Our first consideration is how would we convert no string into no string? Well, that's sort of a base case. It doesn't take any operations to convert nothing into nothing. You don't have to do anything. Nothing is already nothing. But what would it take to convert L into an empty string? Well, in that case, it would cost one operation to delete the L, and then no operations to do nothing else. So once you delete the L, you've got a perfect comparison of a null string to a null string, and it's 0 additional operations. So our cost would be the best thing we could do so far, which was 0, plus the cost of this cell, which is deleting the L. So it would be 0 plus 1, or just a total cost of 1. Now, if we wanted to convert LO into an empty string, that would have a total cost of 2. 1 to delete the O, and then the best solution we found for converting L into an empty string, which was one operation of deleting the L. So we took our solution to converting L to a blank string and added the additional cost from converting LO into a blank string. So we used this solution and just added on this little extra step. That's kind of the key to dynamic programming, is to use solutions you already figured out on smaller problems, L to nothing, to solve a bigger one, LO to nothing. Next, we do the N, and again, this is one operation of deletion plus the best way we found LO, which was 2. So 2 plus 1, or 3. D, same idea. This will be 4, 5, and 6. The overall edit distance to convert London into nothing is 6 operations. And we could trace back what we do. We go left each time, which is a deletion. So we delete, we delete, we delete, we delete, we delete, and we delete all the characters, all 6 of these characters, until we get nothing. And we've converted London into an empty string. That handles that nice base case there. And let's handle the base case in the other direction. So to convert nothing into t, we would have to insert t into nothing, so that we've got a t up here. So it would cost one operation, one insertion of t into our empty string, to turn our empty string into t. Same idea for to. We would have to insert the o into the nothing, and whatever the best way to get t into nothing. So to convert nothing into to, we would need to insert t and o. So 2 insertions. Same idea here. We've got 3, 4, 5, 6, and 7. So it would take 7 operations to convert nothing into Toronto. We would have to insert all 7 of the letters in Toronto into our blank string to convert it into Toronto. And we'd follow the same path we did here. We would say, okay, we did an insertion, and we'd keep trailing up until we got to our empty string to empty string base case, and we'd know that we did 7 insertions. Now, the real heart of it starts, and we see how we can convert actual strings to actual strings, and we get to use these values to the top and the left to help our decision making. The first case here is we compare L to T. Well, L is not T, so it's going to take one operation to convert L into T, which would be a replacement. So we would have 1 plus its best, the best neighbor of its 3 things, either a deletion or an insertion or a replacement. And that would be a 0. So our total cost here would be 1 plus our best neighbor of 0, which is just 1. So it would take 1 operation to convert L to T, a single replacement. Next, we've got LO into T. Well, we look here, O does not match T, so that's going to cost us 1 to delete the O. And our best neighbor is one of these 1s, so it'll be 1 plus 1, or a total cost of 2. We would do a deletion and then a replacement to convert LO into T. We would delete the O, and then we replace the L with a T. Anyway, at each point, we can always trace back our path to see how to find each subproblem. LON to T, again, it doesn't match, so 3, D doesn't match 4, O doesn't match 5, N doesn't match 6. So to convert London into T would be the same thing. It would also cost 6 operations because T doesn't help us. It doesn't get us any closer to London because we have to replace it anyways. In the next row, though, we've got an O. So an O actually will finally help us out. It doesn't help with the L. So TO and L, that doesn't help, unfortunately. So since they don't match, we would have a 1 plus our lowest neighbor, which in this case is a 1 up here, so 1 plus 1, or 2. So it would take two operations to convert L to TO. We have to do both a deletion and well, actually, we would do an insertion and then a replacement to convert TO into L. And Then we look at the next one. So O and O finally match. So this doesn't cost us anything. We finally have no cost, and we'll add in our lowest neighbor, which was this diagonal here. So we'd have 0 plus 1 for a total cost of 1. It would take one operation for us to convert LO to TO. We don't have to do anything with the O's, and then so we go diagonally, and then our L and our T we simply replace and for a single operation to convert LO to TO. Next we've got N and O, so we would need to delete the O, so that gives us an operation. We delete the O, we don't have to do anything, we come diagonally and do the replacement, and we've converted LON to TO. Now we come here to D, D doesn't match, so we have to do 3. We come here to another O, and this is where we could kind of think about it. So we could use this O, but to do so we'd have to go diagonally, because that means we've already used this guy, and we can't use it anymore. So if we come diagonally and we use the O here, we have to go to this node, which is a 4. So we could say 0 plus 4 and go that route and use the O here, and that would mean that we would trace it back and we would end up with this being a total cost of 4 because we used this path. Or we could simply delete the O and use it for this O here. Either would work totally fine, but regardless we end up with a 4, whether we choose nothing and adding this, or a deletion, or an operation and adding the 3. And then our N doesn't match, so again we've got a 5. And let me make this R a little clearer. So this would continue on. L doesn't match R, so it's going to be our lowest of 3 neighbors plus 1, so 3. R doesn't match O, it'll be our lowest of our 2 neighbors plus 1, 2. R does not match N, lowest of our 2 neighbors plus 1, 2. R does not match D, lowest of our 2 neighbors plus 1, 3. R does not match O, lowest of our neighbors plus 1, 4, and 5. So far, we've seen it takes 5 operations to convert London and Tor, 5 operations to convert London to TO, 6 to convert London to T, because we don't have that extra O to help out, and again 6 to convert London into nothing. And we keep filling these out. In this case, we've got another O here. O does not match L, so it'll be our lowest neighbor plus 1 for 4. O does match O. So in this case, we have an interesting thought. We can immediately use it and take the diagonal, or we can insert and go up and use this too. And again, in this case, we would run into similar results where we do 2 plus 1 and get 3, or we do 0 plus 3 and end up at also being 3. Regardless, we end up with 3. Whether we do a insertion plus 1 and get 3, or whether we just do nothing, use the O, and go diagonally. Now we've got another N with the O, so N does not match. We'll have a operation, so 1 plus our lowest neighbor, we've got 3. D does not match O, 1 plus our lowest neighbor, which is, again, 3. And now we've got a nice little O here. O matches O, so we can take our lowest, we can use it here for our diagonal, and we don't have to count anything. So we've got 3, and O does not match N, so it would be 4. So in this case, now that we've got a second O, it's down to only 4 operations to convert London into Toro. These 2 O's can be used, and we do insertions and deletions to fix the remaining letters. And all right, now we've got our N, lowest neighbor plus 1 because they don't match. So we've got 5. O and N, they don't match, lowest neighbor plus 1, 4. N and N do match, so we can consume it, and we're at 3. We would be able to take 0 plus our diagonal and have a nice 3 here. N and D don't match, So this would give us a 4. O and N don't match our lowest neighbor plus 1, so 4. And N do match, so we can again, actually, yeah. So if we took the diagonal here, so let's actually do that out. So if we took the diagonal, we use the N, we use the O, then the D and the R, we delete the D, and then we delete, or we replace, and then we use it, and we replace. Yeah, it would be a total of 3 operations, it looks like. So it's pretty good. And then we keep going, so T, the T and the L, this would be a total of 6 because they don't match. T doesn't match. So for all of these, it's just going to be one more their best neighbor because T doesn't match any of these letters. So this one will be 5, this one will be 4, this one will be 4, this one will be 5, and this one will be 4. And then finally, we've got our O here. So our best O and L don't match. Our best neighbor is going to be 7. And let's see, O and O do match, so we could go for the replacement, so 6 plus 0 for 6, or we could go straight up for the insertion, and in that case, we would end up with the 1 there because we've inserted it, so we would end up with a 6, unfortunately. And since we're not taking the diagonal, in this case here, we've got N and O. They don't match, so we would have our lowest, which is 4 plus 1 or 5. D and O do not match, so we would have our lowest plus 1, 5. O and O do match, and we can take the diagonal. So that would give us a nice 4 here. N and O do not match, so we would end up with a lowest 1 plus 1, or 5. So it looks like we got a total of 5 operations to convert London to Toronto in the best case. And let's see here. I think that's right. Let's double check. So I got my code real quick. I have a little min destination here. Got my Toronto and London simple algorithm for the edit distance. I give it a run. We can see a min edit distance of 5. So it looks like it checked out. We found a minimum distance of 5. And if you want to, it's a very simple algorithm. Handles our base cases and does each of the 3 things at each step. It finds the minimum, so 1 operation plus the best case of either inserting, removing, or replacing. Ends up finding an edit distance of 5 there. And that's what we ended up getting here. We had a total distance of 5 to convert London into Toronto. And we could map it back. We could go here, and here, 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 and here. Oops. To trace back our path of operations that we used to convert London into Toronto. So we did an insertion, replace, replace. Sorry, no, we did an insertion, a replacement, and then a replacement, and we kept that, and a final replacement for our 5 operations. So every time the number stays the same, we're not actually doing anything. And otherwise, we're doing a insertion or a deletion or a replacement depending on the direction. Now you can see there's another route. We could have also gone this way. We could have gone to the 4, 4, 3, 3, 2, 1, 1, 0. So you can have multiple ideal paths that you can backtrack through. Okay, that should have demonstrated the edit distance. Unfortunately, it's really late and I have to go. I'll try to do another video real quick for the third one on the finding paths. But hopefully this made these two clear, and I hope it helped.